Namaste and welcome everybody to the Transitional Artificial Intelligence Seminar Series. This week we have Dr. Ehsan Farahbakhsh from the University of Sydney, who is a research associate at the University of Sydney and also the deputy director of our research group. And Dr. Farahbakhsh is a remote sensing expert, and I had the wonderful opportunity to supervise his PhD. And then since after that, we continued our work together, and also in collaboration with Dietmar Müller, Professor Dietmar Müller, who is also our mentor. So Ehsan will present this research that has been published in the journal Advances of Space Research. Thank you, Ehsan.
Yeah, thank you. Well, hi everyone. Thank you for joining us today. So, as Rohit said, I'm going to talk about our recent paper in Advances in Space Research, which is actually on a framework that we have recently developed for creating geological maps by applying machine learning algorithms to remote sensing data. And to be more specific, we use the dimensionality reduction method, as it is obvious from the title, called stacked autoencoders, and also k-means as our clustering method. And so before I go further into the paper, so let me introduce a bit more. So as Rohit said, I'm a postdoctoral research associate at the University of Sydney, and I hold a PhD in mineral exploration from Tehran Polytechnic, and I joined the Earthwide group at the University of Sydney in late 2021. And my main research interests are data science applications in mineral exploration. And the main project that I'm currently working on is a spatio-temporal prospective modeling of porphyry mineralization, which is known as the primary type of mineralization for copper deposits. My other research interest is multidimensional mineral prospectivity modeling, as well as geodynamic settings and their implications for mineral exploration. Geological remote sensing, the one that I'm going actually to be focused on today, and also exploration, geochemistry, and geophysics. Right, so, and I have some co-authors in this work. So Sandeep actually is the lead author in this paper, and also Joseph and Rohitash, they're actually my co-authors in this paper. And so, as I said, in this work, we used remote sensing data, and we applied some computer vision and image processing techniques. And we focused on a small part of a province, a geological province called Kernamona province, the border of New South Wales and South Australia, which is known for rare earth element deposits. And so the main advantage of using remote sensing data is that you can gather information from some places that it is hard to access them. For example, there's an area which is in a war zone, or there may be some, for example, the area may be, environmentally protected, for example, in this case. So you can actually gather some information from those data, by sensing some actually information remotely. And I don't say, that there is no geological information about this study area, but there is only illegal, information available, geological information available from this area. And we tried actually to employ remote sensing data and create a more detailed geological map for this study area. And so as you see, for example, this is the map that has been provided by the Geological Survey of New South Wales, as you can see here. And we try to improve, the resolution and the accuracy of this map by employing remote sensing data and machine learning. But before I get into machine learning, part of the work, so I actually have put some slides here, to introduce you what introduce remote sensing to you, and go through, some of the data types that we have used in this study. So this is one of the standard definitions that we have for remote sensing, and it says the art, science, and technology of obtaining reliable information about physical objects and the environment through recording, measuring, and interpreting imagery and digital representations of energy patterns derived from non-contact sensor systems. And these sensor systems are categorized into different classes. And here you can see two different types of them, passive and active. In passive sensors, the source of energy, which is recorded, by the sensor, the source of energy is the sun, and the sensor measures the sun, actually the reflected sunlight. But in the case of active collection, or in the case of active platforms, the source of energy is actually mounted on the platform, and the sensor actually measures the reflectance which comes from the objects, on the land or any other surfaces, and that actually a response, is the source of that response is actually is from the platform which is orbiting around the Earth. And but in this study, the type of data that we are using is passive, comes from the passive sensors, and it's also called optical data as well. And this is, the other way that you can classify remote sensing data: optical and radar data sets. Optical, again, there are, kind of passive data, and radar data set that you see, there are kind of active data. And optical and radar data terms actually that you see here, they refer to the electromagnetic spectrum. And for example, you have heard about the visible part of the electromagnetic spectrum that covers from 400 to 700 nanometers, or 0.4 to 0.7 micrometers. And in addition to visible part of the electromagnetic spectrum that our eyes is able to detect, then we have another part of the electromagnetic spectrum which is very important in geological studies, and that's infrared part of it. And in optical remote sensing images, in addition to visible part of the electromagnetic spectrum, images also cover near infrared and shortwave infrared as well. But in the case of radar data sets that we have, they only cover the microwave part of the electromagnetic spectrum. And the advantage of radar data sets compared to optical remote sensing data is that they can pass through clouds or any other element that we have in the atmosphere. So this is the advantage of them. But one of the challenges that we have when we want to process optical remote sensing data, we need to deal with clouds, and we need to remove them from our images, or we need to pick those images that we don't have any cloud covering. So in this study, in this paper, actually, we have used three types of optical remote sensing data, but I will go through them in detail later. And so remote sensing data, actually, they have different characteristics or specifications. So there are different 4 types of resolutions that they are defined for each remote sensing data. We have spectral resolution, spatial resolution, temporal resolution, and radiometric resolution. But here, actually, I go quickly through the spectral resolution, which is the main, actually the most important characteristic of the remote sensing data. And it refers actually to the number of spectral bands that the sensor, can detect. For example, the human eyes, they only can cover, as I said, a small part of electromagnetic spectrum, which is from 0.4 to 0.7 micrometers. But as you can see, as you know, electromagnetic spectrum is much, wider than this. And optical sensors actually can help us to also gather information from other parts of electromagnetic spectrum as well. And here in this image, the gray parts, actually, they are the atmospheric, the percentage of the atmospheric transmission. And it is obvious that we are we are not interested in these areas that are in that. I don't know if you see that. So we are not interested in these areas, that the percentage is 0. So we want actually to be able to record, some signals from the Earth. So you can see that, for example, here you can see different types of sensors that we have here. And the spectral bands, most of them are designed to be located in the portions of the electromagnetic spectrum that we can record response. But you can see we have other, for example, we have some sort of data that they also record in these areas that they're actually used for weather forecasts and also atmospheric studies. But they're not actually our interest, and we prefer to focus on those and use those spectral bands that are located in the gray areas. And so in addition to, for example, your screen of your mobile phones, or for example, this projector, they all use a color system, which is, for example, the famous one is RGB, red, green, blue. And all the colors, they're formed in these color systems by giving, a number to the each of these, channels, for example, from 0 to 255. You can create, several different colors. But you can see that in addition to a range of, red color, green color, and blue color, we have other, spectral bands that they cover, other portions of electromagnetic spectrum. And using these spectral bands that they cover, different ranges, we can create, false color composite images in addition to images that our eyes, can see them. So this is, another advantages of using optical remote sensing data. And so in this study, we used three types of remote sensing data: Landsat 8, Aster, and also Sentinel-2 data. That I quickly will go through, these data types that we have used. So Landsat is the name of a program which is actually sponsored by the NASA, and it was launched in 1972. And it includes, 9 satellites, and the 10th satellite is going to be launched in 2030, sorry. And it is not called, Landsat 10. Either they are going to call it, Landsat Next. But and among, these 9 satellites, actually the only one that couldn't reach to the orbit, was Landsat 6. And the 2, satellites that are still active, they are Landsat 8 and Landsat 9. And the rest of them, they're not operating anymore. And so these are actually Landsat 8 and 9. Landsat 8 actually was launched in 2013, and Landsat 9. So Landsat 8 was launched in 2013, and Landsat 9 in 2021. And they're very similar in terms of spectral resolution. They're almost the same, and they have this almost the same set of sensors that they are called operational land imager, that they cover the visible and near infrared part and of the electromagnetic spectrum, and thermal infrared sensors that they have actually they cover in 2 portions of the thermal infrared region in the spectrum. And we use and these 2 bands, they're not that important for us in geological studies. And we focused on using the rest of the spectral bands, that we have in these specific remote sensing data. And so in this study, we only use Landsat 8 data, since the Landsat 8 and 9, data that we have, they're very similar to each other. And the advantage of Landsat 9 is that it's higher, radiometric resolution only. And in terms of spectral resolution, as I said, both of them, they provide the same spectral resolution, or the number of spectral bands. And it's interesting to know that actually each of these spectral bands is a feature for us. And later that I will start talking about the machine learning. So the features, our features would be the spectral bands that we have here. For example, in the case of Landsat 8 data, that we have 11 spectral bands. If we remove, 2 thermal infrared bands, we'll end up with 9 bands, that are actually inputs to our machine learning workflow. And in addition to Landsat data, we use Aster data as well. There is a satellite, called Terra, on which we have 5 different sensors have been mounted. And one of those sensors is called, Aster. And it covers, 14, different parts of the electromagnetic spectrum, as you can see here. And it's very important for geological studies, due to these bands, that you see here. And they cover short-wave infrared part of the electromagnetic spectrum. And this part of the spectrum is important to us, for geological studies, since most of the minerals that we have, they show a specific behavior, spectral behavior in this part of the spectrum. And the other actually data set that we used was Sentinel-2 data. And Sentinel, similar to Landsat, which was launched in 1972, Sentinel includes, 10 satellites. And so they're not numbered, Sentinel 1 to 10. But, we have, for example, 2 Sentinel 1 or 3 Sentinel 2. It's like this. Actually, to reduce the revisit cycle, actually to make the revisit cycle actually shorter, or increase the frequency of revisit cycle. So you will have more, for example, when you use actually Sentinel-2 data, since we have 3 satellites in this actually constellation, Sentinel-2A, Sentinel-2B, and Sentinel-2C, the revisit time actually is 5 days. So you will have a similar image, for specific locations each 5 days. So it's very important for example, for in land cover mapping, for example. And in this, but most of the Sentinel satellites, they're radar satellites. But in this study, we're interested in optical data, and the only satellite in this constellation that provides optical data is Sentinel-2. So we used Sentinel-2 data as well as Aster and Landsat 8 data. And so the thing about Sentinel-2, the interesting thing about that is Sentinel-2 actually provides the highest resolution, highest spatial resolution among all 3 satellites that we have. So it was the advantage of using the Sentinel-2 in this study. And we were interested in seeing that does the spatial resolution of satellite data, they can influence the accuracy of geological maps that we create or not. For example, the spatial resolution of Landsat is 30 meters, and also Aster data provides 15 meters resolution, but Sentinel-2 provides 10-meter resolution. And we were interested in seeing, can it affect, the accuracy of our geological maps or not? And the spectral resolution of these, 3 types of satellite data that I mentioned, they're almost the same, from 11 bands to 14 bands. So the spectral resolution was the same. So I'm pretty sure, that you all know about dimensional reduction in machine learning. So I'm not going to much talk about this. But in remote sensing data processing, for example, in this case, we have used multispectral data. But sometimes you need to process hyperspectral data that provide, over 200, bands. And in other words, you will have over 200 features, and you need to use dimensional reduction actually to reduce the dimensionality of your feature space. So they're important actually, since high dimensional data can actually be computationally intensive, as well as they're prone to noise, and also they're challenging to analyze. So in the remote sensing community, it is very common to use principal component analysis, as it is very common and also popular, and also I can say it's effective. But we were interested in testing some new ways actually to reduce the dimensionality of our feature space, and that was the main motivation for us. And we started looking at different methods that were available. So, and we got interested in autoencoders. And then we realized that there is a more efficient a type of autoencoders called stacked autoencoders. And we tried, and compared, principal components and canonical autoencoders, as well as, stacked autoencoders. And so, as you might know, autoencoders, they consist of an encoder, as you can see, for example, in this image that we have here. So they have an encoder actually that compresses input data into a latent representation. And we are interested in that actually latent, space representation, or we call it latent vector as well. So we actually took that latent vector as input to the K-means clustering instead of the original image, with, for example, 13 or 14 spectral bands. And it also, in the structure of autoencoders, we have a decoder as well that reconstructs the input from the representation or the latent vector that I mentioned. So, and here actually at the top, you can see, 3 false color composites images, of that we have used in this study. For example, Landsat 8, Aster, and Sentinel-2. And as I quickly actually mentioned, the spatial resolution of Sentinel-2 is 10 meters. Aster is here actually is 15 meters. Landsat 8 is 30 meters. So we used actually all these, those spectral bands of these 3 different types of remote sensing data as input to our workflow. For example, but the thing is that we remove, for example, thermal bands from our study, since they cannot be very helpful in our for creating geological maps. And we took the latent vector, as input to the K-means clustering. And but this is actually the structure of the canonical autoencoder. But in the structure of you can see that the structure of stacked autoencoders is a bit different from what we have in the canonical autoencoders. And as you can see here, they're composed of multiple layers of interconnected autoencoders, where the output of one actually autoencoder serves as the input for the next one. And by employing stacked autoencoders, it allows actually us for more create more to do more sophisticated feature learning and also abstraction, as well as stacked autoencoders. They are also effective in capturing complex patterns and representations in large data sets. For example, when we cover actually a large area, and we want to create geological maps for a large area, so stacked autoencoders can be very efficient to increase the ratio of signal to noise. So that was another motivation of using stacked autoencoders in our study. And so we actually designed a framework that you can see here. So it starts, with data acquisition. That these three types of data that I mentioned, they are freely available from USGS website or Copernicus website, which is sponsored by European Space Agency. And after applying radiometric and geometric corrections or any other required type of corrections to the images, they're scaled, so they can be normalized or they can be standardized. So in our case, we standardize all the spectral bands of our images. And then we used three types of dimensional reduction methods: principal component analysis, as well as canonical autoencoders and stacked autoencoders to reduce the dimensionality of our feature space. And then we employed K-means to create cluster maps. But to determine the optimal number of clusters, which needs to be introduced to the K-means algorithm, we used elbow method. And using elbow method, we determined the optimal K for the K-means clustering. And then when we actually created, those, and when we got those clustered maps, we used majority filter, to reduce actually noise in our data. And then we got, our final map. So on the right side, actually, you can see that different pairs of remote sensing data, as well as dimensional reduction that we had in this study. So as I mentioned, we used Landsat 8, Aster, and Sentinel-2 data, and 3 dimensional reduction methods, including principal component analysis, canonical autoencoder, and stacked autoencoder, that resulted in 9 different clustered maps. And so the thing is that the number of clusters, actually the optimal K that we achieved, using elbow methods, they different for different pairs of remote sensing data and dimensional reduction that we use. And they varied between 6 and 7. And so some of our cluster maps that you can see, they have 6 classes, and some of them, they have 7 classes. And we used 2 different metrics to evaluate the performance of different pairs of remote sensing data and dimensional reduction method, as you can see in this table here. And one of them is called Kalinski-Harabas, and the other one is Davis-Boulding. In the case of Kalinski-Harabas, it actually the higher the value, the better the result. But in the case of Davis-Boulding, that shows the similarity between 2 clusters. The lower, that's better. So and you can see that the combination of stacked autoencoders with Sentinel-2, when we compare these results, it results in the best actually performance. And the only type of data that was able to assign a specific cluster to vegetation was Sentinel-2 only. And so we realized actually that actually spatial resolution can play a role, actually significant role, when we want to create a geological map using by combining clustering and remote sensing data. And later we tried actually to interpret these cluster maps that we have got here by using ground truth data. So we used open source data that are provided by Geological Survey, for example, of New South Wales, to help us with interpreting the clusters that we see here. And we compared, these clusters, the location of them, and the areas that they cover with known geological, geological knowledge that we had. So we actually access to a database of ground truth data, and they include actually a few points that you can see here. And each of these points, they represent a specific rock type or a geological unit on the ground. So they're listed here, and we could actually, to relate each of these rock types or geological units to one of the clusters that we had. So you can see that one of these classes, it only includes vegetation, and the rest of them, which includes five, it includes, 5 different types of rocks or geological units, from volcanic units, to, for example, the plains that we had in the study area. And the other thing that we did was we also evaluated the performance of the combination of different dimensionality reduction and remote sensing data types, but by calculating overall accuracy, and which is the ratio of the samples that have been clustered correctly, and also the total number of samples that we had. And again, we saw that the combination of stacked autoencoders and Sentinel-2 resulted in the highest one. Also you can see that the combination of stacked autoencoder and Aster data, it also resulted in accuracy of 0.9, which is actually significant. And so to summarize this study, so we tried actually to combine machine learning with remote sensing and try to use a different dimensionality reduction methods compared to previous studies. And also, the other problem that we have in remote sensing studies and also in geological studies is that we cannot always use supervised learning to create maps, since most of the time it's hard to access data, since, for example, the companies own the data and they do not publish that publicly, and so we don't have much data actually to train our models. So most of the time you need to use unsupervised learning in your work. So that's what was another motivation for us to use unsupervised learning in our study. And also based on our study and the results that I showed you, we realized that the combination of Sentinel-2 and stacked autoencoders actually it outperforms the other combinations of satellite data and dimensionality reduction methods. And so it would be actually good for the community, to also give a chance, to other dimensional reduction methods like stacked autoencoders, for dimensional reduction instead of, we're using PCA, for example, which is very well known in the community. And also using developing maps, by using such framework, they can also provide some new, geological interpretation of the structures that we have in our study areas, and also they can provide some geological information, new geological information from different study areas. And so this workflow is completely open source, and it's available on our GitHub repository that you can see here. And I would be happy, for those of you who are online, and if you're watching, this video on YouTube or elsewhere, and if you have any questions, so I would be happy to answer your question through my email. And yeah, that's it for now. Thank you. Yeah, sure.
Like, we want to know where is the code, where is the data, how you process the data. Like, if somebody in machine learning is there who does not know about remote sensing, how do they approach it?
Yeah, we have 3 Jupyter notebooks here, for Landsat 8, for Aster, and Sentinel-2. For example, I open Landsat 8 here. And the data sets, they're all available here. If you go to data sets, so you can see that we have volcanic rock units. These are the rock units that we have in our study area. They're actually our ground truth data. And in the main data set, you can see that we have Sentinel-2 and Landsat-8 and Aster data. And if I quickly go through the Jupyter notebook, so we import, the libraries that we need. So we used actually scikit-learn as well as, TensorFlow in our workflow. And so we load our data here, then we employ, principal component analysis first, and then we apply a elbow method to get the optimal K value. And then we employ, k-means here, for example. This is the map, created PCA and k-means. And then here we have canonical autoencoder. And so again, as I mentioned, we use TensorFlow to create actually our neural network here. And so here is our elbow method again, and we use the latent vector as input to the k-means. And for example, here the optimal value is 6. So here is the map created using canonical autoencoder and k-means again. And then we create, our stacked autoencoder, and we employ that to create our, latent vector. And you can see that we have 3 consecutive, autoencoders here: the first one, the second one, and the third one. And again, we use elbow method to determine the optimal K. Optimal K here, you can see that it's 7, not 6, in contrast to the previous one. And then we imply k-means again, to create the clustered map. And yeah, you have also this option to save, these maps into a GeoTIFF file. So if you know how to work with QGIS or ArcGIS, you can open the georeferenced clustered map in the GIS software packages and create, and change, these colors that you can see, or create a professional, map, by adding scales and other, north arrow and other things there. And yeah, and the rest of the notebooks that we have here, they are similar to this one, but we use different types of data. And as I said, you can access the data in the datasets folder here. And yeah.
Thanks, Ehsan. So we take some questions from the floor and questions, comments.
Just not about the word as such, but why don't you label the different categories? Like, you must have had somebody that said this is vegetation, this is different minerals and that sort of thing.
Yeah, actually, we relied on geological reports and the information that are currently available. So we realized, that each of these points, they fall within a specific cluster. And then we labeled the whole cluster, based on that. And as you can see, there is only a few ground truth samples, available in the study area. And the resolution, for example, here we have a geological map with the resolution of 10 meters, which is unprecedented. So I can say this is the highest resolution geological map that ever created for this specific area, using Sentinel-2 data, and also by getting some data, from the geological surveys as well.
Just a quick point, the spectral resolution, its ability to distinguish between the resolution.
Yeah, spatial resolution. Yeah, I meant yeah.
No, when you are talking about the spectral resolution,
yeah.
It should be the spectral category or the spectral range.
Yeah, Sentinel-2 actually, that you can see that this map is based on Sentinel-2 data. It provides 14 spectral bands, which is also interpreted as spectral resolution. So it covers, spectral electromagnetic spectrum in 14 different ranges. Right. And at each range, the sensor measures the average response that it gets from an object on the Earth's surface. Since for example, if for example, a spectral band covers from 100 to 105 micrometers, nanometers. So at each of these, 101, 102, 103, the sensor there, we have some sensors that can detect that and measure the response. But in multispectral sensors, they average, the whole response that it gets, at each of these values. Yeah, and yeah, as you correctly mentioned, we have 4 different types of resolutions. I didn't go through that here in detail. in addition to a spatial resolution and spectral resolution, we also have temporal resolution and also radiometric resolution that they also refer to different things. And but here, in this study, the thing which was more important was what the spatial resolution, and we were interested in comparing the data sets that they provide different spatial resolution. So in the future, I think in the future projects, we are going to use hyperspectral data, since previously, we didn't have access to free hyperspectral data easily. But in 2022, a satellite was launched called Nmap that provides over 225, I think the images they have over 220 spectral bands. And they provide a spatial resolution of 30 meters. So they can be very helpful in even mapping minerals, specific minerals on the ground surface. But the problem is that in an area 30 meter by 30 meters, you don't have a single mineral. You have a mix of different minerals. So you get a mixed response to the sensor. It would be hard to interpret, but they can be still helpful. For example, for mapping alteration zones, there is a specific type of geological units that we know that they're related to mineralization. And since these days, critical minerals are getting more and important for us, for renewable energies. So such technologies can help us to address, for example, these problem and issue. Yeah.
Thanks, Ehsan. Other questions? Okay. Yeah.
So, I so say here you use the Landsat and Landsat 809 and U2. Have you considered to use the recently launched harmonized Landsat Sentinel?
Landsat 9, you mean?
Yes.
No.
Harmonized, I think
yeah, here we use Landsat 8, Aster, and Sentinel-2. But when we actually started this, this study, I think Landsat 9 was not launched, I guess. And that's why we have done actually another study, and used convolutional neural networks. We applied that on Landsat 9 data to map alteration zones that I quickly mentioned. And but in this one, we haven't used Landsat 9, only Landsat 8. And as I said, the advantage of Landsat 9, as you might be aware of that as well, is the higher radiometric resolution that it provides. So instead of 8-bit, I think it provides the resolution of 12-bit.
I just wanted to comment that very good work with the GitHub repository and the code examples. That's a good example for other members of our group on how to document code and data. Just a comment about this image that we see here. So it's a 10-meter resolution. Ehsan, how many megabytes of data is this, and what's the size, like in kilometers?
The size, actually the unit for these numbers that you see, they're in meters. So it's around 30 kilometers, I guess over 30. I can say 40 kilometers by maybe 50 kilometers.
Okay, so it's a fairly big area that you see. And how many megabytes or gigabytes, I think it was?
No, it's not gigabytes. It's only, I guess, it's a clustered map. So we have only, 4 or 5 classes. I think it's 20, 30 megabytes.
30 megabytes.
Yeah, it's not that large.
So the process can be extended to larger maps.
Yeah, sure. Right. Yeah.
But in the case of larger maps, note that the autoencoders have the limitations in terms of the larger the training data, the larger the training time it will take.
Yeah.
So there needs to be kind of batch processing, and instead of usual PCA, you may use incremental PCA and other things. So Ehsan, I have a question for you. There's these other methods such as TSNE and UMAP, which you have not considered. Like, what do you think? How do you think they would be behaving in this?
So we are actually working on another project in which we have evaluated different the performance different dimensional reduction methods, and we have tested 6 or 7 different dimensional reduction methods on benchmark data sets. Like there's a famous data set called Indian Pines, for example. And that study is not yet finalized.
It's a hyperspectral data.
Yeah, it's hyperspectral data.
So we have an evaluation paper that will be released next year.
Yeah.
So we have 2 papers, and in another paper we are also comparing different clustering methods.
And in there, we have compared UMAP, TSNE, PCA,
Yes.
And yeah,
I completely forgot that we already done that. Yes.
Yeah,
Thank you,
yeah,
Ehsan.
yeah.
So just a bit of a yes.
Apart from this questioning algorithms, do you think it is feasible to consider segmentation methods?
Yeah, sure. Yeah, yeah. I think in the future also it's also another idea that I have
Yes.
for the future was to use segmentation instead of clustering at
I mean,
signal.
what clustering is doing generally for image data sets is a form of segmentation, right? That's what you have done in reef core analysis. But then there are other segmentation, deep learning based segmentation methods, which is computationally more difficult, but you can take sliding windows or sliding, what do you call it? Chip. That's
Yeah.
chip is the
We use it in CNN.
sliding boxes, basically.
Yeah.
So just want to say that there was when we started this project, I recall that I was actually not working at UNSW. I was actually working from Centennial Park.
Yeah.
Now I remember. And then we had Sandeep who joined as an intern, and this started in 2021, and finally it got published.
Sometime.
Yes, it got published in 2024. And so, and the review process was also more than a year. So,
Yeah.
thanks, Ehsan, for making sure all this is done. And thank you, everybody. Just a second. Anybody has any questions online for us? Okay, I can see my mentor Christian there. Hi, Christian. Right, and okay, catch up with you all later. Take care. Bye-bye.
Bye.